This video presents a study on tactile perception, exploring how humans and robots detect objects buried in granular materials like sand using only touch, inspired by natural systems like shorebirds. Tactile detection in sand relies on sensing subtle force changes to locate hidden objects before direct contact. The wide zoom model explains tactile sensing in granular materials. A finger disturbs particles in a wedge-shaped region, calculated from its size and sand properties. As it nears a buried object, additional forces signal its presence before contact, enabling early detection for both humans and robots. Human experiments use a sandbox with 4 fixed locations, where a cube could be buried or not at all, to keep participants unaware of its presence or location. Finger sizes were measured for each of the 12 participants to calibrate the wide zoom prediction. After familiarization trials, participants inserted their index finger vertically into the sand, then rigged forward at a constant speed, guided by an LED strip for consistent pressure and trajectory. They stopped as soon as they sensed the object before contact, with stopping positions recorded relative to the cube across 18 trials per participant. Robotic experiments mirror the human setup using a custom tactile sensor, sized similarly to a human finger, mounted on a unified robot arm. The sensor featured 4 taxels, detecting 3D forces. The same sandbox, sand type, depth, and speed were maintained. The cube remained fixed, but starting points varied to generate diverse trajectories. Force data were collected until 2 cm from the cube across 120 trials for training LST models with distance-based labels. In object-absent trials, participants correctly identified no object in 58 of 72 cases, with false positives appearing random. In object-present trials, the wide zoom model predicts an average detection range of 6.9 cm, marked in orange. When the cube was in location 1, most stops occurred within this predicted range before direct contact, and this pattern remained consistent across all locations. Robotic models detected within the 7.1 cm wide zone, with lower thresholds providing precise, timely stops and minimal false positives. Higher thresholds led to broader distributions and premature detections in absent cases, confirming the model's validation through false data patterns. Comparing the 7 cm threshold robotic model to humans, robots exhibited a slightly wider detection range. Humans demonstrated superior precision in object-absent trials, with fewer false positives than the robotic system.